Assalamualaikum and good morning to panel of examiner and everyone. My name is Norizin Azira binti Rushidin. Today, I will talk about my poster presentation of research project 2 with the title Effect of Sodium Alginate and Calcium Carbonate in Synthesizing of Zero-gel-based active fruit bunch via overdrying in absorption of engine oil. I will proceed with my poster presentation. This is my poster presentation for this research project 2, which consists of abstract, objective methodology, results, and conclusion. Abstract section. This research focuses on the possibility of zero-gel-based EFB as unabsorbent on engine oil with effect of chemical, sodium alginate, and calcium carbonate. This research provides a comparison in terms of physical structure, absorption capacity, and shrinkage percentage between the standard ratio zero-gel and varying parameter zero-gel. The problem that led to this research are the environment of pollution that caused by the spillage of oil into land, river, and ocean, the disposal EFB that affect the soil due to the high carbon and nitrogen content, and lastly is the inefficient and high-cost technology in separating the oil. The amount of chemical use influences the absorption capacity and percent shrinkage of zero-gel. As a result, zero-gel-based active fruit bunch is a viable adsorbent for engine oil. This paper has been submitted to the Journal of Environmental Chemical Engineering Q1. The objective for this research are to synthesize the zero-gel-based active fruit bunch EFB via overdrying with the effect of sodium alginate and calcium carbonate. Secondly, to characterize the result zero-gel by SEM, PET, FTIR, XRD, and TGA, and the absorption of zero-gel-based EFB using engine oil. In the methodology section, it is divided into 3 sections, which are the preparation of EFB, preparation of zero-gel, and absorption of engine oil. For the preparation of EFB, procedures are taken from Abdul Wahab with few modifications. The palette shape active fruit bunch EFB were reduced by using ball milling and blend using a mixer. Then, the blended EFB was placed in a sieve tray. Proceed with the preparation of standard ratio of zero-gel EFB, where 0.5 gram of sodium alginate was dissolved in the 50 ml of distilled water with a constant stirring 600 rpm. Then 0.15 gram of calcium carbonate was added into the solution until fully homogenized. Next, 0.5 gram of EFB was added into the solution for 10 minutes before adding 0.15 gram of GTL into the mixture for 30 seconds. Then, quickly pour the solution into the mold. The gel is cooled in the cooler for 24 hours to allow for gelation. After 24 hours, mass and volume of hydrogel were recorded. The steps are repeated for each parameter, which is sodium alginate and calcium carbonate, with different weight percent. The hydrogel then is placed in a universal oven with a constant temperature of 60 degrees Celsius for 24 hours to produce zero-gel. After 24 hours, the measurement of mass and volume of zero-gel are recorded. Next is the preparation of absorption test based on the ASTM. The adsorbent was put into the beaker with a tweezer in a 15 ml of used engine oil for 15 minutes. Next, the adsorbent is taken by using a tweezer and placed at the top of the empty beaker using a net strainer and drained for 30 seconds. The adsorbent weight was calculated and recorded. The procedure was repeated 3 times to obtain the average value for comparison and more precise tests for later on. Now, we'll proceed to the next result section where we discuss on finding of synthesizing and performance of zero-gel-based EFB. This figure shows the physical structure of zero-gel with the effect of sodium alginate and calcium carbonate. The increasing of sodium alginate resulting in darker color of zero-gel and becoming more harder, which shows from figure 1A to figure 1C, while in figure 2 shows the effect of calcium carbonate to the physical structure of zero-gel. By decreasing the amount of calcium carbonate, resulting in thinner, brittle structure and more transparent color from figure 2C to figure 2A. Alginate is an anionic compound which is capable of forming gels in the presence of Ca2 plus ion released from calcium carbonate with the presence of GDL. Dissolved in the alginate solution by internal gelation method. This figure shows the effect of sodium alginate on adsorption capacity and percentage shrinkage. The increasing in the amount of sodium alginate will decrease the adsorption capacity and also the percent shrinkage. This is because increasing in alginate only improves the structure of adsorbent, but lowering the adsorption capacity and also percent shrinkage due to the increasing of pore size and pore volume, which based on the PET results. The decrease in alginate will result in increasing of adsorption capacity because of the effective cross-link information of gel with equivalent ratio of calcium carbonate and GDL. This result is similar to Raj-Mohan, which obtained decreasing of adsorption capacity and percent shrinkage when increasing the amount of alginate due to worse of stability structure. This figure shows the effect of calcium carbonate on percentage shrinkage and adsorption capacity of engine oil. It was observed that decreasing trend of adsorption capacity and percentage shrinkage as the amount of calcium carbonate increasing. According to Osberg, amount of calcium carbonate should not be in excess than alginate and GDL. This is because the increasing amount of calcium carbonate will affect the gelation process, thus decrease the percent shrinkage and adsorption capacity. Calcium carbonate is relying with the amount of GDL and alginate. GDL will help the release of calcium ion and cross-link with alginate for the gelation process. The decreasing in the amount of calcium carbonate will increasing the adsorption capacity due to the effective of internal gelation process. Next, I will explain on SEM result. SEM is used to characterize the porous material by analysis on the surface morphology. In this figure, show surface morphology of zero-gel-based EFB with various magnification range. In the first figure, it was observed that the surface area of raw EFB is rough and rigid, consists of a highly ordered arrangement of the fibril. The strands of EFB show some crack and formation of micropores that result from lignin removal and allow for adsorption of engine oil. While in the second figure, display the surface morphology of blank alginate zero gel that shows smooth surface and homogeneous structure. This blank alginate zero gel sample shows a flexible structure which are easily bent without a breaking that happen due to the diffusion of calcium ion by internal gelation. Figure 3 shows the XEFB with various magnification. It can be seen that many EFB fiber attached in unalginate are maintaining its shapes and consist of pore. The addition of EFB to alginate causes change in the microstructure of zero gel. According to Hidayu, the activated EFB carbon contribute to 90% micropore of the total pore volume and the presence of tiny mesopore. In figure 4, show the raw EFB, XEFB, and blank alginate zero gel at magnification of 500x. This figure focuses on the production of XEFB using internal gelation process. In the A figure, show the fibrous structure of EFB, while B figure show the flat surface and homogeneous structure, and figure C display a fibrous structure and smooth surface with a combination of raw EFB and blank alginate zero gel sample. This morphology of the XEFB can be concluded that they consist of aggregate of small fibrillar network which are interconnected into pore and has a brittle structure. Hence, the internal gelation and drying process are completed. This table shows the surface area, total pore volume, and pore size for all samples from BET analysis employed with nitrogen gas. It was observed that standard zero gel shows insignificant change of surface area, pore size, and pore volume, while blank alginate zero gel display a high BET surface area and pore volume by decreasing pore size than raw EFB. The standard zero gel has low surface area and high pore volume compared to other sample due to the gelation process. Next, regarding the effect of chemical use, the decreasing individually of sodium alginate and calcium carbonate resulting in the increasing significantly pore volume that lead to high absorption capacity. In conclusion, the quantity of chemical also influence the pore size, pore volume, and surface area that contribute to the absorption capacity value. Figure in the left side show XRD pattern consists of raw EFB and xerogel EFB. The peaks of both samples display the presence of cellulose type 1 and lignin structure. Besides, the raw EFB shows the presence of crystal cellulose structure at sharp peak 22.17 degree, which similar from previous study. The XRD pattern of XEFB show broad peak because of amorphous material due to the chemical use in internal chelation process, while figure on the right side show TGE curve to compare the thermal stability of the sample and is divided into few regions. The first region is at temperature 39 degrees Celsius to 50 degrees Celsius show raw EFB release high amount of moisture content compared to blank alginate and xerogel. The next region show the first degradation of blank alginate due to release high amount of volatile matter compared to other sample. This is due to alginate release high amount of hydroxyl group and alginate backbone was breaking along increasing in the temperature. While the third region shows the degradation of all sample occur at temperature of approximately 900 degrees Celsius. Next, figure on the left side was observed. The raw EFB shows the OH stretching that indicate the presence of phenol and alcohol, while xerogel EFB show diminish of OH stretching because of mass loss happened during drying method. Xerogel EFB display the presence of C double bond O stretching indicate the presence of hemicellulose and lignin after the internal gelation and drying process. Both of the sample display the CO stretching indicate as any hydroglucose chain, while figure on the right side show the OH stretching that exists in xerogel does not appear in blank alginate. There are several peaks that appear in blank alginate spectrum that represent the presence of CH stretching, C double bond O vibration that indicate the presence of carboxylate ion, and CH bending. As conclusion, xerogel-based EFB successfully synthesized by internal gelation method via overdrying for absorption of engine oil. Xerogel EFB is characterized by using SCM, FTIR, TGA, XRD, and BET. The morphology of xerogel EFB consists of a fiber network which is interconnected leading to a pore and smooth surface. By decreasing in alginate and calcium carbonate individually, the pore volume will increase. After the internal gelation and drying process, the wavelength of 1734 per centimeter appear indicate the presence of hemicellulose and lignin. By decrease, the ratio of sodium alginate or calcium carbonate will increase the absorption capacity of engine oil and percent shrinkage. The highest absorption capacity for xerogel EFB is 0.69, whereas the highest percent shrinkage for xerogel EFB is 99.1%. Hence, xerogel EFB is capable in absorbing engine oil, thus it is a valid absorbent. My recommendation for the next researcher who interested in furthering this study is to use a different parameter, such as the effect of contact time between the engine oil and the absorbent, and effect of temperature towards the absorption of xerogel on engine oil. Besides, the drying method can use a supercritical drying or freeze drying instead of conventional oven. Last but not at least is the use of various engine oil on the absorption of xerogel-based EFB. I would like to express my special thanks of gratitude to my supervisor, Prof. Dr. Azil Bahari alias, and our coordinator for research project who gave me the golden opportunity to this wonderful project on the effect of sodium alginate and calcium carbonate in synthesizing of xerogel-based EFB via overdrying on absorption of engine oil. I will also like to thank my parents and friends who helped me a lot in finishing this project within the limited time. I am really thankful to them. That's all from me. Thank you also to the examiner for evaluating my poster presentation. That's all from me. Thank you to the panel of examiner for evaluating my poster presentation. You may contact me for the Q&A session. Thank you.